Hi and welcome to this installment of By Manufacturers Direct, Execs and Techs, where we sit down with industry experts and innovators to discuss trending topics concentrated in the surface preparation industry. In this ongoing series, we'll examine traditional methods and best practices, as well as review our industry's most popular pieces of equipment, while taking a peek behind the curtain of the engineers and manufacturers who build them. We'll also explore and experiment with commonly used products in addition to introducing new cutting-edge technology. Joining me each episode is our resident subject matter expert, former contractor, and current substrate technology president, Josh Jones. Each episode, Josh and I will discuss various aspects of our industry. We'll explore topics from both rudimentary and experienced perspectives in an effort to advance the knowledge of both beginners and seasoned veterans. Throughout this series, we'll ask our audience to help identify and nominate future discussion topics by subscribing to one of our online platforms and submitting your suggestions in the provided comment section.
Hello, my name is Kevin Hawthorne, and thank you for joining us for this installment of Execs and Techs, our continued educational series exploring various facets of the surface preparation industry. This being our first segment, I thought it would be helpful to review some of the fundamentals surrounding our industry. Joining me this week is industry patriarch and substrate technology president, Josh Jones. I hope you find this segment informative and beneficial to your business.
My definition of surface preparation would be basically getting the substrate, in this case a concrete floor, ready and in a condition to accept an epoxy or a polyaspartic or urethane coating to absorb and bond. Basically, that means profile would have to be created that's to the specification of the product, and also, or equally as important, would be the absorbency of that surface so that that coating can absorb in and basically grow roots like trees or grass grow roots in dirt, so it fuses itself to the concrete surface.
Okay, so you said a lot of terms there that might be new to the audience. So I think before we jump into discussion, it might be helpful for us to kind of go over and just define some of the key verbiage and words that are used in our industry. If you don't mind, I'll ask you some questions and you can just kind of give us your interpretation of those phrases or words. So Sure. What exactly is a substrate?
Well, substrate is just kind of a catch-all term for, in our case, a concrete floor. When we consider the floor as the place where the coating is actually expected to perform, bond and perform, I'm going to generally refer to the floor as the substrate. But it basically just means, in our case, concrete slab or floor.
Okay. Another term that's very commonly used is, that I've heard, is called surface profile. What exactly is a surface profile referring to?
Basically, it's referring to how rough the surface is. And the reason that's important is because some coatings, as they cure and cross-link and harden, go from a liquid state to a hardened state, they create tension. And when that tension takes place as the reaction occurs, the idea of the profile that's created is it almost acts like a Velcro. So as that coating starts to create tension and starts to pull against itself, we want it to pull against itself as it pulls into the floor or bites into that texture. Now that's all created in the formula by the manufacturer of the coating, which is why they specify a certain kind of profile. But again, essentially it's to get the coating to bond to the floor, almost like Velcro grips to itself.
Okay, and a lot of the online trainings that I've looked at, they use the phrase scratch pattern. How is scratch pattern compared to per profile? Is it the same? Is it different? Is it just semantics?
It's hard to say. It depends on the context when somebody says scratch pattern. Normally, scratch pattern is a conversation had with regard to polishing, because the scratch pattern needs to be removed and refined. In the case of a coating, the coating doesn't really know how to discriminate between one scratch and another. If it's specified as an example, a CSP2, concrete surface profile 2, generally speaking, in terms of what's accepted in the industry, that is a diamond grind. The substrate, the concrete hardness, and then the variation of diamond tool that's used is going to greatly influence that so-called scratch pattern. If it's a 16 grit, if it's a 30 grit, whatever grit diamond it is, the way that the substrate is going to respond has a lot to do with its hardness and its natural makeup. So scratch pattern doesn't really factor into a profile conversation, but there is something to be said for, the trails or the marks that are left behind after diamond grinding.
Okay, well, that brings up actually a good point. You said CSPs, concrete surface profile. So CSP basically is a standard measure of roughness defined by the International Concrete Repair Institute. Can you go through a little bit and describe what CSP is, and why is it important for a contractor to understand what it means and how they achieve the certain CSP measurements?
Sure. CSP, concrete surface profile, is on a numerical scale. It goes, I believe, 1 to 9. When it comes to floors, in my experience, we really don't care too much about anything above a 5, because in most cases, anything higher is going to be for like pressurized tanks, fluid containment, stuff like that, where it's more important to have that kind of profile for that coating to bond. On the lower end, which is where most thin mill coatings are going to come up against these types of profiles that are specified, the number 1 is basically just trowel concrete. That basically means no treatment whatsoever. Clean, maybe absorbent, but no actual texture. Concrete surface profile 2, generally speaking, is going to be a diamond grind. They're in the samples that they have, the chip kit they have, you can actually see scratches in the floor that would indicate it was a diamond ground surface. CSP3 is a shot blast, which is more like a sandpaper finish. There's really no pattern to it, but there you can see that there's a uniform roughness to it. CSP4, some people will say it's a heavy shot blast, which is basically just a more aggressive profile. So let's say CSP3 shot blast is going to be like a 60 grit sandpaper. CSP4 is going to be like a 30 grit sandpaper. So the elevation inequalities between the high and the low in the profile, the roughness on your hands or to the coating, is going to be greater as we go into that number 4. Bush hammers can also be used for that. But again, it's just a matter of making the surface more aggressive to some standard that the manufacturers have specified so their coating can bond like Velcro. That's all been formulated in that product. And then a CSP5 is a scarification, which is quite a bit rougher. It doesn't look like sandpaper as much as it actually looks like grooves in the concrete. How deep or the grooves are, or the inequalities between the peaks and the valleys of the grooves, really depends on the substrate, the machine. But then after that, as it goes up from there, there's really just variance of that as it gets more and more rough. So 1 through 5, 2 through 5 actually is where we really are going to find most of the coatings that most people are using these days are going to rely upon for what's been specified by the manufacturer.
And I think you touched on it. And one of the things that we'll touch on in future episodes is matching certain mechanical preparation or methods with certain CSPs. Based on the roughness that the manufacturer is recommending. So, for example, like you'd mentioned, to get a CSP5, the right mechanical method might be a scarification, because it might be beyond that of what a grinder can do, and might be beyond what a shot blaster can provide. So, and we'll talk about this in future episodes as far as what's the proper, or what is the what's the recommended mechanical process for each CSP. And with a little bit of variety in there, but we'll touch on that with each piece of equipment as we get into future episodes. So talk a little bit about, now we've just touched on mechanical methods. There's also the chemical side. Typically, the most common are the chemical or mechanical methods of profiling a floor. What are the differences, advantages, disadvantages? What should a contractor be aware of when he's walking into a specification, and there's more than one method to achieve whatever he's trying to get to as far as CSP?
Well, the only other chemical method that I can think of that is still around and still used would be acid etching. So that's really the only other chemical method that I know of. And in my experience nowadays, when I see specifications, technical data sheets, I see a lot of times where they say acid etching is not recommended. So I don't know how often it's going to be that a manufacturer would say that they prefer an acid etch. But acid etching does work. It does attack the surface of the concrete because it is an acid. So, of course, it reacts with the calcium in the surface of the concrete. It erodes it away and makes a profile. And then after that, it's neutralized and cleaned. And now you have a profile, assuming that the specification says that that is acceptable. So some will say acceptable, but not recommended. I think the verbiage should be all mechanical, but certainly there is another way to make a profile, but that would be with that chemical method.
If I'm a contractor just venturing into the industry, and I'm going to one of the big boxes and I'm buying a product off the shelf to put down in a garage floor, for example, a lot of those instructions will include either acid etching or pressure washing. would you consider pressure washing a viable option for surface preparation?
I'll always defer to the manufacturer. If the manufacturer says that pressure washing is acceptable, they'll usually also specify the amount of power that washer has. They'll advise on, further more to the process, what else has to take place, whether it needs to be fully dry, just the surface water blown off. So I wouldn't say it's a bad thing if a manufacturer says their product will work with a pressure wash. Now, when it comes to resinous coatings, there's really no difference among manufacturers when it comes to resinous coatings in the way that they are meant to fuse or bond to the surface of the concrete. It's by absorption and by texture. If the pressure washing creates enough texture, or maybe the slab inherently has texture already, but also cleans it out enough that there is now absorbency so that the coating can soak into it, well, once it's dry, I mean, that in theory could be an acceptable method. In my experience, though, when it comes to high performance coatings and the way that they cure and the performance that's expected from them, normally they're going to recommend, again, mechanical preparation to whatever CSP has been specified, probably with a strong recommendation to not do acid etching. But I would always follow the manufacturer label. If that's what they say should be done, then I would follow the manufacturer. But I think more times than not, even in DIY type products, it's going to be specified that the surface be sound, it be clean. Maybe they'll mention, especially DIY products, maybe they'll mention CSP, because really, I mean, if it's DIY, they would have to figure out where the customer is going to get this equipment, because now it's going to be specialized equipment. So the manufacturer always has an out in their specification that says clean and sound and dry. Clean means contaminant free. Sound means there's no loose substrate present, so that when the coating bonds, it bonds to something solid. And as far as it being dry, I mean, that's obvious. It needs to be dry because you're usually putting down a petroleum-based product. But when it comes to dry, same thing. The manufacturer said dry. Whether or not it sticks is really going to be up to the person that prepares that slab.
Right. Let's talk a little bit about contaminants. I recently attended a seminar with some coating manufacturers, and they were all in agreement. One of the worst things you can do is apply a coating, regardless of the brand, if there's any kind of contaminants on the surface, because that will basically prevent a bond from occurring between the coating and the surface. And a contaminant in their interpretation could be anything. It could be dirt, it could be concrete dust left behind in the mechanical process, a lot of minor airborne things that are hard to control. Based on your experience, what do you think are the contaminants, and what's the best way to control that or to collect those, so when you do apply your coating, those contaminants have been removed?
Well, after the mechanical surface preparation, if there's oil, if there's silicone's a big one because that'll cause fish eyes. It's very difficult to remove that other than with grinding or mechanical means. Really it comes down to anything that's going to inhibit the absorption of the resinous material when it's in a liquid state. Anything that slows it down from absorbing into that concrete, it's not going to be able to go in there and actually grow those roots. So as that material starts to cross-link and harden, we want it to be inside the surface of the concrete. So whether it's concrete dust, which concrete dust, mineral dust from grinding, needs to be completely removed, because the coating was never specified or formulated to mix in with whatever random dust has been left behind and somehow consider it to be structure. It's not, it's contaminant. Now, it may not cause a problem when it absorbs into that, and they do add wetting agents to coatings to be able to handle human error in the real world. But ideally, all that dust should be removed. When it comes to any oils, any film forming products like Cure and Seal, there again, it's inhibiting the penetration of that resinous coating before it starts to harden. We want it to be able to soak in. Oil, silicone, like I said, silicone is something that's tough, because if it gets there by cross-contamination, walking from one area to another, the coating can fish eye, which is obviously going to cause a blemish, maybe not a performance issue, but certainly it's not going to bond, it's going to have a blemish. So anything that's on top of the concrete that is not a part of the slab is an unknown. And whatever that unknown is could be a future liability. When it comes to mineral dust and moisture, possible moisture instigated issues later, that is a different topic, but it is related, because from a manufacturer standpoint, if I have a failure, and usually it's going to be a delamination, and I pull that sample from the surface and there's concrete or anything stuck to the back of the coating, it's surface prep. It's going to fall back on the contractor, and the manufacturer's product did not fail. It just did not bond because what it was bonded to is stuck to the back of it. And that's not a part of the slab.
Okay. And we will touch on these subjects in greater detail in future episodes, but one of the things that has come up in initial conversations regarding proper bonding or adhesion of a coating is moisture in the slab. So how do you, A, determine that there's moisture in the slab, and B, how do you contain that or remove it so it does not cause a failure of the coating after it's installed?
That's a great question. There's a lot of contention when it comes to moisture testing, and the biggest reason that I found from all the people I've talked to about it, professionals that do it, as well as the manufacturers that make the products, there's really no way to duplicate a moisture instigated failure in the laboratory to know exactly what can be done to protect oneself against that failure. There are steps that can be taken to protect the contractor. The contractor should take it upon themselves to protect themselves, to test for moisture vapor evaporation rates, which is a calcium chloride test, a very old test. Some people will say it's too old and it doesn't work, it's archaic, but it does measure a certain amount of moisture vapor transmission over a time period. That is one insurance, let's say, against a future failure, that the contractor has at least empowered themselves with some information that before they poured it, they have an actual test that's been done that shows they've done some due diligence. The next test is a relative humidity tester, which basically is going to monitor the amount of moisture that's inside the slab to whatever depth the probes will measure. And there's a lot of different machines or ways to do it with the different meters that are out there. But in Google, you can find all these different things. But basically, it's trying to measure how much humidity, how much moist air is inside that slab at the time of pouring, whether it's, in the current climate that it's going to be poured. So there's a whole methodology to testing it to get reliable results. That is another insurance method to basically say, I have done my due diligence. I've tested for moisture these two ways. So that's good. You just do those tests and record them, assuming they fall within line with the product and what its specified tolerance of moisture is. If it falls in line, then the work has been done from the standpoint of protecting against moisture that could possibly cause a failure later. Then there's a pH test. A pH test is basically going to say what the chemical nature of the concrete slab is at the time of placement, and pH test should be done after the floor has been prepared, and it's in the prepared state that it's intending to be coated at. So that means basically if I intend to grind and shot blast, before I put the coating on, if I want to get an accurate pH test or a reliable reading, I'm going to do the test right before I put the coating on, because I need to know what the pH is that the coating is going to be attaching itself to. So whatever that surface is that I've cleaned and prepared, that is where the coating is going to land. So that is the one I need to know the pH of, not when I, first do a walkthrough, obviously not after a failure, but the idea is we're trying to prepare that surface and know it's in a chemical state that the coating is not going to have any interaction issues with. That's all in the technical data sheet as well, of what the range of pH can be for the coating to be able to perform, so it doesn't have any chemical issues. It also can give a better picture of the current state of the concrete. I think cured concrete that we'll say is healthy has a range between 9 and 12 pH. Very alkaline, but that is what I think healthy concrete comes in at. If I find that my pH is way low, it could be because there's a chemical solvent in there. It could be because there's some other issue going on. There could be structural instability that acidic nature, let's say, of that surface is indicating. I don't want to be a part of that failure, because if I pour my coating on something that is not proving out to be structurally stable, despite all the work I've done so far, I don't want to put a coating over it, because that would be as a contractor, that would be my responsibility. Now that I've done these 3 tests, I've got all this data and everything seems to check out. I go ahead and go for it. If I go ahead and put the coating down and I do it per the manufacturer's recommendations and nothing goes wrong, then fine. At least I have that data to show that I've done the due diligence, and it's a good practice. If I have a problem, I'm going to be much better prepared to call a manufacturer and say, we have a problem. We don't know why it went bad. Here's my data. And this is from the manufacturers that have told me this. A manufacturer looks at this much differently when a contractor says that a coating has failed versus I have a failure. I have all my test data. I don't know why it failed. I need help. Act of God, a flood, whatever it might be that has happened, a contractor is going to be in a much better position to get backup and support from the manufacturer, because as their frontline defense for their image and their brand, they've done the due diligence to protect that brand and their own credibility that they verified the slab was in a condition that was suitable for that coating. If they've done that, they've got an ally in the fight. Again, nature, we can't control nature ever. But by doing that, it at least shows that there is some, they're working in a conscientious way before they go ahead and put somebody else's product down. Because if the product fails, everybody's on the hook, everybody's involved. So doing that little bit of work ahead of time is going to ensure that in the case of a failure, they're not going to be hung out to dry. And that's how they'll feel. But the truth is they might not have done the due diligence that would have stopped them from applying the coating in the first place.
Talk a little bit about the misconception as far as the application of a coating can be done at any time of the year, in any climate, and anywhere geographically. Obviously, the humidity factor in an area like Miami is much different than a Seattle, Washington. So talk a little bit about how the climate can affect the coating. And is there an ideal time or ideal temperature to do an installation? Or are the guys in Minnesota restricted to only the summer months to do something to not guarantee but improve the chances of a better adhesion? Or are the coatings becoming so sophisticated now that that factor has been eliminated from the equation to where there is any coating, anytime, anywhere type of scenario?
That's a really good point. In the technical data sheet of any product, any reputable product, any product I've seen is going to give an acceptable application range in terms of temperature, humidity. They'll probably direct to watch for check the dew point before application, because we're dealing with a product that is going to chemically react. It's going to chemically react either by heat, by humidity, combination of both. But these are products that require their environment to influence how they behave once they're combined. They're reactive materials. The most important thing I would think, besides reading the technical data sheet, which is going to give all the readings at a fixed temperature. So as we move away from that temperature, higher or lower, things will go faster or slower. Besides that, it's really a matter of knowing the product and how it behaves. If I don't know the product I'm using, and I'm let's say 10 degrees away from the temperature that it's specified to be applied at, I personally would be making a call, and I have made those calls. I know that I've seen temperature ranges down to 60. My slab temperature is 55. I call the manufacturer, and the manufacturer usually will say it can do it, it can handle it. It's going to be slower. 4 hours cure time for tack-free dry at 72 degrees. It's now going to be 8 hours at 55 because it's a natural material. It is a chemical reaction. So the colder it is, usually, the longer it'll take. The warmer it is, the faster it's going to go. Now, fast is okay, but the problem with fast is if it goes so fast that I can't get it applied to the concrete fast enough based on the heat, meaning it's going to start to cure or start to react, I should say, before it's able to do that absorption into the surface, it might not absorb as deeply as it needs to. So the failure, again, is not a coating failure. It's an application failure because the coating actually started to react and thicken before it hit the surface and was able to absorb in. It's difficult for contractors to try to get their head around it, but you think about a product that let's say at 72 degrees, it's like warm pancake syrup. At 60 degrees or 55 degrees, let's say it's now twice as thick because it's cold. Well, as I go warmer, now it's all of a sudden, let's say it's instead of 72, it's 80 degrees. It's even more runny. So that's good. I mean, it's good that it's got a low viscosity because it wants to soak in. But what I have to keep in mind is now that material is more warm, when it mixes together, that reaction is going to be that much faster. And all of a sudden, this resinous liquid material turns into something that is harder than concrete. That turns into 7,000, 10,000 PSI material. So we go from a very liquid state, depending on the temperature, to something that is literally rock hard. And that's where temperature and humidity and dew point, that's why Mother Nature is so important to consult. And we've got all kinds of apps now and all kinds of technology that helps us with this. But that's why it's so important to know exactly what that natural environment is, whether it's inside a climate controlled area, and we know what that environment is in terms of temperature, humidity, whatever, or if it's exterior or uncontrolled, we very much need to know what that air temperature is, that slab temperature is, the humidity, dew point. Because these are all forces that are going to come into play as this material tries to do its thing. And it will do its thing, but will it establish the right amount of strength? Will it fuse to the surface of the concrete before it does that. That's the science behind what ultimately turns out to my floor looks good or my floor is delaminated. So yeah, the natural elements are a huge influence, or are going to be a huge influence over how that product reacts once it's mixed.
Well, it's great. Josh, this has been a great discussion. I've learned a lot. I hope our audience has too. And just so they know, we're going to be focusing on a lot of different topics that center around surface preparation and coatings and the proper best practices for installation. We're going to have a lot of industry guests, what we call execs and techs, executives and technicians from our industry, to dive into specifics about their products and their segments of the industry. So we look forward to continue the discussion in the next episode. Josh, thanks for the time, and we'll see you next time.
Sounds good. Yeah, it was great. I really appreciate the opportunity. Thanks.
Absolutely. Thank you for sharing your time with us. If you enjoyed today's educational installment and would like to be notified when we release new segments, click the subscribe button below. If you'd like to suggest a topic for a future episode or have questions pertaining to this week's subject matter, please feel free to leave us a comment. And as always, we invite you to visit us at buymanufacturersdirect.com to view tutorials or purchase some of our industry's most respected and recognizable brands.